Hello everyone, my name is Cojocaru-Mirédin and I'm group leader at the First Institute of Physics of RWTH Aachen in Germany. So the lecture today is about the thermal effects and field evaporation of molecular ions and multiple events. So before starting, I would like to tell some words about me. So I have performed my master and the PhD studies at Rouen University in France. Then in 2009, I joined the Max Planck Institute für Eisenforschung in Düsseldorf, Germany as a postdoc, and I had worked intensively with the CHS thin film solar cell and the atom probe tomography. Then between 2013 and 2015, I was the head of the interface design in solar cell group at Max Planck Institute für Eisenforschung in Düsseldorf. Then since 2015, I'm the head of nanocharacterization of advanced functional materials at the First Institute of Physics of RWTH Aachen in Germany. So my key research areas are advanced functional energy materials like solar cells, phase change materials, and thermoelectrics. So this lecture is based on several books and papers that I have presented here on the slide. Of course, you'll find some slides without any reference, which means that actually these slides are built up upon our own experience. So this lecture is composed of four main parts. So I will speak about thermal effects first, and I will focus on the laser-matter interaction. Then I will speak about field effects, and I will give some possible models for the molecular ion formation. You will see in all these books and papers that there are several terms used for the molecular ion formations, and these are molecular ion, complex ion, and cluster ions. They are basically the same thing. Then I will speak about data analysis implication, specifically for the mass spectra, where we end up with a lot of molecular ions available and will then lead to a difficulty to have reliable compositional data analysis. And finally, I will speak about multiple events as a fingerprint for unconventional bonding mechanisms. So let's start with the thermal effects. And I wanted first of all to discuss about possible phenomena which can take place when a laser arrives or illuminate the atom probe tip. And there are several phenomena which can take place based upon the pulse duration. And for example, these phenomena are, the pulse duration is actually given here below. So we have a pulse duration between femtosecond to microsecond. And we have here four different phenomena which can take place. The first one is carrier excitation, which is basically the absorption of photons, which give us photogenerated carriers like electrons and holes. And we are going to speak later on a little bit more in detail about that. Then we have thermalization, and this is a very important concept, since this process actually is the one which leads to the heat inside our sample. And because we have heat induced, of course, we speak about phonons, and then we speak about scatterings. So we have carrier phonon scattering processes or carrier scattering processes. And then because we photogenerate electrons hole pairs, so we have an excess of charge carrier inside our material, then this excess needs to be somehow removed. Therefore, we have recombination phenomenon. And we have mainly two possible recombination phenomena. The first is the radiative recombination, and the second is the Auger recombination, which is a non-radiative recombination mechanism. And I will speak later on a bit more in detail about that. And finally, we have thermal and structural effects. And these are processes which take place for pulse durations which are between picosecond and microsecond. So, of course, we are not within our atom probe LIP system, we are not on the microsecond regime, but we might be here 10 to minus 11. So in the 10 picosecond regime, so we might be actually here in this regime, and we might speak about thermal diffusion processes. So again, our LIP system has a pulse direction of about 10 picosecond. And this means that all these phenomena that I have talked, the 1 to 4, are really possible, especially the 3 first one, are really possible to take place for our system, for our material when we analyze with a LIP system. Okay, let's go and speak about absorption of the photons. So what we have, so the principle of absorption is the fact that when we have a semiconductor material, the energy of the photons should be higher than the band gap of the semiconductor material. And this condition is presented here. So we have the energy of the photons, which is h mu. Mu, it's the frequency, it's simply given by the ratio between the speed of light and the wavelength. So, and this ratio, so h times c over lambda, should be higher than the band gap of the semiconductor material. And then we have absorption. So what that means? So it means that the energy from the photons is absorbed by the material, and we have the excitation of the electrons from the valence band to the conduction band. So we have the photogeneration of a free electron hole pair. So we can also say, actually, so again, the condition is that, and this is a very important aspect, that the condition that the energy of the photon should be higher than the band gap, or we can also say that the wavelength should be smaller than the ratio of Planck constant times the speed of light over the band gap. So for our LIP system, this is not a problem, since we know that the wavelength of the laser that we are using is pretty small. So most of the systems are nowadays either green laser or UV laser with a wavelength of about 300 to 550 nanometers. So this requirement is fulfilled so that we have maximum absorption by our semiconductor material. Let's speak about thermalization process. I was speaking before about the absorption process. And the thermalization process happens when we have absorption, but happens for the photons which arrived with an energy much higher than the band gap. And so this energy would be enough actually to photogenerate an electron from the valence band to the conduction band. But because the energy is very high, it means that the electrons is going to reach very high energy levels into the conduction band. Of course, this scenario is not into equilibrium, and the system would like to relax. This electron would like to relax to the band edges, to the conduction band edges, and we have the release of the energy as a heat. And these are our phonons. And this explains actually how the thermalization process is a process responsible for the heat induced in our atom probe tips while we investigate such samples. So because the thermalization takes only a few picoseconds, the thermal model works well for any material that is excited with the laser pulses of picosecond or longer duration. So we know that the pulse duration for the LIP system is about 10 picosecond. So that means thermalization process, it's a process that it cannot be avoided. I told you that we might also have recombination mechanisms. And this is simply because we have an excess of charge carrier inside our semiconductor material. And we have two main recombination mechanisms which can take place. The first one is the radiative recombination, which is actually a process which is the opposite of the light absorption. So in the radiative recombination, we have a recombination between the electron from the conduction band and the hole from the valence band. and we have the emission of the light. This is simply the same as we would have a light emitting diode device, where we have radiative recombination and we have light coming out of the device. So it's exactly the same principle. Now we have another non-radiative recombination, which is not anymore a two-particle process, but it's a three-particle process, because the energy release after recombining an electron from the conduction band and a hole from the valence band, it's released to a third particle. This can be either an electron in the conduction band or a hole in the valence band. And because these electrons are going to reach much higher energy levels, again, we are going to have the same thermalization process. So we are going to have a loss of the energy in very small steps and release this surplus of energy as a heat inside our sample. So again, recombination inside our sample can also lead to supplementary heat inside our atom probe tip. So the fourth mechanism that we were talking about is the thermal effect. And there is a very nice work done by Sanduram and had published recently in Nature Material. And they have shown actually that the laser fluence is a very important parameter. And if the laser fluence is too high, then we reach a certain threshold for irreversible structural changes. And it means that our material is going to be completely changed structurally. So the band gap is going to collapse and the band structure is going to change. Now, the LEAP has a UV laser fluence below 0.5 kilojoule per meter square, which means that we are not reaching these irreversible processes. So this is a good message for us. But we are actually in the region where we would have a lattice heating. And the authors had shown actually how by increasing the threshold, we can induce the heat, and they quantify the heat induced actually inside a gallium arsenide semiconductor material. And if we are approaching 50% of this threshold, so we see here this curve, we see that after a time delay of only almost 10 picosecond, a temperature of about 1000 Kelvin can be reached. And this is definitely a temperature which approaches the melting point of some of semiconductor materials. So definitely this is something that we want to have not happen inside our atom probe experiments. Now there is a very old work done by Draxel in Germany, where they have shown actually that when we reach these very high temperatures, melting temperatures, we might have the formation of the molecular ions on the mass spectra. And they show nicely this for three different metals, for gold, silver, and copper, that on the mass spectra we have the formation of gold 3, gold 2, or gold 4 molecular ions. And the same goes for the silver and the copper. And the only explanation for that was that the laser energy was so high that it had induced a very high increase of the temperature, a temperature above the melting point of the metal. And this is how they explain actually the formation of these molecular ions. But now there are some very nice experiments which have been performed by Kelly and co-workers, and they have measured actually the temperature at the apex of the tip. It is important to mention here that compared to the work of Sundaram, they have measured the temperature increase on the sample when the sample was kept at room temperature. Our atom probe experiment are actually cooled down at cryogenic temperatures between 20 and 70 Kelvin. This is a very important condition. And Kelly and co-workers measured the temperature at the apex of a tip, of a silicon tip, and they found out that the temperature cannot go beyond 150 Kelvin. And of course, the temperature at the apex of the tip is a sum of two contributions. the temperature of the specimen, and a ratio between the temperature, peak temperature reached by illuminating the atom probe tip with a laser, and a term which is given by the thermal diffusivity and the volume of the heated zone, sigma. So that means actually that the work that I have shown you before, that actually the formation of molecular ions is due to the melting temperature, cannot be the reason for the experiments where we see molecular ions using modern atom probe tomography. Of course, we have some thermal effects, and this we see very nicely when in mass spectra of the silicon tips, where we have this thermal on the mass spectra, and these thermals are sometimes impossible to be avoided. So if the lattice is only slightly heated by the laser, then what is really the reason behind the molecular ion formation? But before talking and speaking about that, and going to the next session of this lecture, I would like to conclude this first part with some conclusions. First of all, we have seen together that number of phenomena take place when a laser illuminates a tip. And we have talked about absorption, thermalization, and recombination. In modern atom probe tools, the thermal effects are strongly reduced so that irreversible phenomena, and we have talked about lattice disorder and band structural change, this phenomenon should be definitively avoided. And we have also seen that thermal effects only cannot be the reason for the molecular ion formation. So let's speak about the field effects and what is the correlation between the molecular ion formation and the field effects. So there is a very nice work done by Batisco and co-workers, where they have shown for the gallium antimony compound the formation of a very high fraction of molecular ions. And we see here on the graph the presence of various molecular ions. So if I take now a laser pointer, I can show you actually that we have antimony 5 in pink, antimony 4 in green, antimony 3 in violet, and antimony 2 in here in blue. And the fraction of these molecular ions can be increased or decreased based upon the applied field. So if we increase the field, the fraction of these molecular ions progressively decreases, while the antimony single ions here are increasing. So there is definitely a strong effect of the presence of the molecular ions and the field. And there was a very old model given by Kingham and co-workers about the mechanism of ion formation in liquid metal ion sources. So what is a liquid metal ion source? It's an ion source which uses metal that is heated to the liquid state and used to form an electrospray to form ions. So an electrospray Tyler cone, it's formed by the application of the electric field, and ions are of course produced by field evaporation. And this is exactly what happens in the focused ion beam for the gallium source. So why the gallium was chosen? Simply because gallium has a very low melting point and a low vapor pressure. And if we now use the same model and try to explain the formation of the cluster models, this can give us, of course, some hints. So if we have here a Tyler cone or a tip-shaped specimen, and we place a very high electrical field here on the apex of the tip, of course, we have possible post-ionization processes, and this we can see it on the mass spectra, the presence of a double charge or triple charge ions. But we have also the field evaporation of some clusters like M2+ and M3+. What it can also happen is that from the side of the tip, we have thermal evaporation of neutral atoms and clusters. Some of them will escape, so will be lost, of course, but some of them will be attracted by polarization forces and are going to be attracted here to the region where we have a high electric field, and these clusters are going to be charged. So this is a possible phenomenon which can be explained for the gallium antimony. And but what is important to note here is that the molecular ion formation in the liquid metal ion sources is predominantly a field effect. If we take some other example of semimetals like antimony and bismuth, we have seen the same behavior in our lab. So we have seen indeed the presence of molecular ions and how this the fraction of molecular ions changes very much when we increase the field. So we see typically that the fraction of these molecular ions decreases when the field is going to increase or when the laser energy is going to be decreased. So is the molecular ion formation mechanism the same as we have seen for the liquid metal ion source model? So typically high evaporation field atoms are retained on the surface of the tip. Then they are subjected to the thermal activation surface migration and form molecules or multimers. And these molecules, because they are less tightly bonded to the surface, then they are isolated. They are easily field evaporated. So, however, this model cannot really explain what happens for some of the semiconductor material like chalcogenides. And I'm going to give you a series of examples of chalcogenide materials, and they are used in many applications. So people had not given much attention to this class of material, but they are nowadays more and more used for the memory application, for solar cell, for thermoelectric. So they are really very important class of materials, and we need also in the atom probe to understand the physics behind application of the atom probe on this kind of materials. So let's start with the copper indium gallium diselenide. This is a photovoltaic material. It is known to have a very high absorption, so it absorbs easily the light, and it also photogenerates easily electron-hole pairs. But what we see on the mass spectra, simply we have a pretty high fraction of molecular ions, like selenium-2, copper-selenium, copper-2 selenium, and there are many other molecular ions on the higher mass-to-charge ratios. If we then calculate a fraction of these molecular ions, we typically get a fraction of about 32%. Now, if we take the silver antimony telluride, this is a thermoelectric material. It contains antimony, and we can suspect, of course, that it has also a very, very high proportion of molecular ions. And we see here nicely that we have all possible statistical molecular ions that can be formed, like antimony telluride, antimony to tellurium, antimony to tellurium-2, and so on. And if we calculate the fraction of the molecular ions present in this material, so we have about 63% of the total ions. So we have a very high probability to field evaporate ions, not single ions, but molecular ions for this material. And the third example, it's a GTE compound. This is a phase change material used for memory applications. And for this compound, we have the same, the presence here on the right-hand side of a huge amount of molecular ions present on the mass spectra. And the total number of these molecular ions is about 45%. So for all these three examples, we can see, in fact, that we have a pretty high proportion of molecular ions, and this cannot be avoided by applying different parameters during the atom probe analysis. Of course, we can change the fraction of them, but they cannot be at all avoided on the mass spectra. So another important aspect is that Of course, the temperature play a role, but it's not the main driving force for the formation of the molecular ions, since the peak temperature measured, for example, for the silver antimony telluride, where we have the highest fraction of molecular ions, about 60%, we measured a peak temperature of about 175 Kelvin. So this is a pretty low temperature on the tip. Of course, this peak temperature measurement might not be that reliable. We might have a big error while measuring this temperature, plus minus 40 Kelvin, as it was stated by some of the authors. But still, this temperature is low enough, and we are far away from the melting point, so that we promote the formation of molecular ions. Okay, so what is really the model which explains the formation of molecular ions at such low temperature and low fields for the semiconductor material? So another important aspect for chalcogenide material is that the field is not that high. So it's typically half of the field applied for metal. So we cannot really say that the field, it was so high that we have promoted actually the formation of molecular ions. And if the field were so high, of course, we would have also the association of these molecular ions while during the evaporation path. So let's speak about field penetration. And I think this is a very important concept, especially for the semiconductor material. Let's start with the metal, because this is our basic material that we work in our lab. So when we speak about field penetration for the metal, so we speak about screening phenomenon actually. This is determined typically for metal by Thomas Fermi screening length. And the formula is given here below. So the screening length, it's inversely proportional to the number of states per unit of volume. But the number of states actually is defined by the electron gas model, as usually we do. And this is directly proportional to the electron density. Now we know for the metal that the electron density is pretty high, and this is about 10 to the power 21 or 10 to the power 22 number per centimeter cube. So that means for the metal, we have in general a pretty high number of states. Pretty high number of states, if we insert here in this formula, means that pretty low screening length. So this is the reason why actually the penetration depth, the field penetration depth in the metal is really very low. And this is about 0.1 angstrom or 0.1 nanometer. So this is really, really a very low number. So that means that the field stays only on the surface and it penetrates only very little inside the metal. And that means only the atoms at the very surface of the specimen are exposed to the electric field. And this also explains why we have a very controlled field evaporation process, that we have atom by atom and layer by layer field evaporation process. And this is also explained why we have mostly single ions and we don't have molecular ions on the mass spectra. So now if we go to the semiconductor and we speak about the field penetration depth, we represent this concept by the Debye length in general. But the problem, of course, is that Debye length doesn't take into account the fact that we have a field applied on the tip. And we have another, there was developed another effective field penetration depth by Song and co-worker, where, and the equation is given here below. So in this equation, it's nicely shown actually that the effective field penetration depth is directly proportional to the electric constant and inversely proportional to the effective mass of the electrons. So the dielectric constant, it's a very important parameter, and we know that this parameter can vary a lot within the semiconductor or insulator materials. So for example, if we take neural bandgap materials used for the memory application, like phase change materials, they have the electric constants, which is 2 or 3 orders of magnitude higher than the standard semiconductor material like silicon. So of course, a much higher dielectric constant means also a much higher penetration depth. And I will show you at the end of this lecture how this can have an implication in terms of physics or in terms of bond breaking within the atom probe measurements. Then we have also the effective mass of the electrons. Of course, if we have wide band gap materials, so we have very big difference, or we have a very less probability to have an overlap between the minimum of the conduction band and the maximum of the valence band. So that means in this case, the effective mass of the electrons would be simply the same with the constant mass of the electrons that we know. But for narrow band gap materials, the effective mass of the electron will be simply very different than the mass of the electron. So here it's also very important to take a particular attention actually to this parameter. And there was a very nice work actually which have been shown dependence between the effective mass of the electrons and the band gap, and they seem to be directly proportional. So if we have a very small band gap, we have a very small effective mass of the electrons. So small effective mass of the electrons, we have a very high penetration depth. And this really nicely shows actually that the depth of field penetration is slightly deeper for semiconductor with narrow band gap. And if we want to have some quantitative numbers, for example, I have found in the literature work where they have shown the field penetration depth for silicon and germanium. Of course, they are not narrow semiconductor materials, so they have a band gap of about silicon of about 1.1 electron volt. But although they have pretty modest or pretty large, moderate band gap, we have a pretty high field penetration depth of about 2 nanometers. This is definitely much higher compared with what we have seen for the metals. And if we want to see now a certain correlation between the fraction of molecular ions and the band gap, since we work in our lab with many chalcogenide materials, I have drawn here actually the fraction of molecular ions for several chalcogenide materials based upon their band gap. And we see here that we have copper, indium, gallium diselenide material. This is a photovoltaic material as I have presented before, and has a band gap of about 1.05 or 1.04. And then we have other material used for the typically phase change material like GTE. The thermoelectric community also start to use this compound for their applications. And we have here basic thermoelectric material like lead telluride, bismuth telluride, and silver antimony telluride. And we see nicely that there is a certain trend between the fraction of molecular ions and the band gap. And again, this is simply because having a lower band gap, we have a lower of effective mass of the electrons, lower effective mass of the electron, we have a high field penetration depth. And this explains a higher field penetration depth might be a reasonable explanation why we end up to have a higher fraction of molecular ions on the mass spectra. So definitely this is a new research area, and we need in the future to explore the interlink between the band gap of material, the fraction of molecular ions, and the field penetration depth. There are other important aspects like the band bending and field-induced metallization. And this had been shown nicely for the oxide material like MgO clusters, but also for the zinc 26, oxygen 26 clusters. And what it had been shown, it's basically the fact that the band gap of this cluster decreases as we increase the field applied on them. And it decreases so much that we arrived at a certain point where we have no band gap. And the same had been observed actually for the zinc oxide, zinc 26, oxygen 26 clusters. So we have a gap, HOMO-LUMO gap, which varying. And then for a certain electric field, high electric field, this gap is going to decrease so much so that it approach actually 0 eV. So this is what we call typically band bending. And this is what we call actually the point where we have an insulator to metal transition, so or metallization point. But let's see more in detail what is a band bending. So here we have typically a band diagram of a semiconductor material. And we know in the bulk that we have the valence band and we have the conduction band and we have the Fermi level somewhere sitting in the gap. At the surface, we have said that we have a band bending. So, but let's see why for the atom probe tips, we have an upwards band bending and not a downwards band bending. So we know that during the atom probe experiment, we apply positive voltage. Positive voltage means positive electric field. Positive electric fields mean that we have, so also from the second equation here, positive electric field means that we have positive charges. So we have here positive charges sitting on the surface of the tip. So how these positive charges are created? It's simply by bending upwards the valence band and the conduction band. So if we bend enough upwards the valence band, we will see that we are going to cross the Fermi level. We know that all the states above the Fermi level are free states. So it means that we create a lot of positive charge holes here on the surface of the tip. And this is why we have positive charges actually where we have an upwards band bending on the tip. Now the metallization point is the point where we bend so much the valence band on the surface so that it reaches this point. So this point is actually the point where we have the conduction band in the bulk. So, and this is the point also where the Fermi energy level will be more or less sitting in the middle of the valence band here in the on the surface. So this is how it explained actually that we can say that actually on the surface of the atom probe tip, if we bend so much the valence band and the conduction band, we get a metallic surface. So now if I summarize what I have said in terms of field penetration depth and molecular ion formation, we can state actually that for the metals, we have a very low field penetration depth. And this explains why we have the absence of molecular ions on the mass spectra, where when we use actually regular standard modern atom probe tools. And for the semiconductor materials, this is the opposite. And we have seen that the field penetration depth is strongly dependent on the parameters like band gap, the electric constant, mass effective mass of the electrons, and of course this also gives us a very different fraction of molecular ions, but definitely for semiconductor materials we have in general much higher penetration depth, field penetration depth than the metal, and this explains why we have not always but very often molecular ions on the mass spectra. So there are also some other effects. So for example, we know that the laser is hitting the atom probe tip on the side. So that means that we have potentially an inhomogeneous laser hitting on the apex of the tip. So if the laser is coming from this side, that means we have a higher heat here induced inside our sample. So that means we'll have a lower field on this side, although on the other side we will have a higher field. So we have an inhomogeneous field distribution on the apex of the tip. And because of this inhomogeneous field distribution, if we have now molecular ions which are going to be evaporated, so here on this side we are going to see on the detector event histogram a decent proportion of molecular ions. And on the other side, because the field is much higher, these molecules are going to dissociate, and we are going to see a much lesser proportion of these molecular ions on the detector event histogram. So how to avoid to have, in general, to have asymmetric tip shapes and also inhomogeneous laser heating and also inhomogeneous field distribution on the apex of the tip? It's simply by fulfilling two strategies. First of all, we need to reduce the peak temperature on the tip. And there was a nice work done by Müller and Cojocaru, where they showed actually that by increasing the diffusion length, we decrease the peak temperature on the tip. So if we increase the diffusion length to 50 nanometer, for example, and this represents actually the radius of the tip, then we have a decrease of the peak temperature to 100 Kelvin. So this seems like a reliable work and a reliable strategy that need to be fulfilled. Now there is a second strategy, it's to increase the pulse duration. And we see nicely how the diffusion length is strongly dependent on the pulse duration. And we can increase the diffusion length from 1 to 1000 nanometers simply by increasing the duration of the pulse from 10 to minus 13 second to 10 to minus 7 second. Of course, increasing the pulse duration might also induce some other phenomenon, non-desirable phenomenon, as we have discussed at the beginning of this lecture. So before ending the second part of the lecture, I would like to make some conclusions. And I hope it was clear for you that the field penetration depth is important, and it's a really important parameter to be explored for molecular ions formation. And the field penetration depth is also strongly dependent on the physical parameter of the semiconductor materials like band gap and the electric function. There are also other potential effects, and we know that we have in general an inhomogeneous heat distribution inside a tip, and this also can explain why we have an inhomogeneous field. So we generate, of course, an inhomogeneous shape of our tip, and then we have an inhomogeneous distribution of the field on the apex of the tip, and therefore we have an inhomogeneous distribution of the molecular ions on the detector. Let's go and speak about the data analysis implications. And this is specifically very important when we have many molecular ions on the mass spectrum that we get. So I will show you here an example of two compounds which have been investigated, like copper indium gallium diselenide and zinc sulfide. And this is typically the region on the mass spectrum between 62 and 69 Dalton. And what we have a peak overlap between the copper, zinc, and sulfur 2. And actually, if we want to decompose this mass spectra in this region, what we would get is something like copper, which looks like that, with zinc and looks like that, and sulfur 2 looks like that. So we typically see that we end up to have an overlap between these three compounds. And this is the reason why it was till now impossible to investigate the interface between these two compounds, which represent the p-n junction in our device. And of course, understanding the physics of a p-n junction and understanding the composition of a p-n junction, it's really very important for the device performance. So these peak overlaps definitely hinders us to have a reliable compositional value at the interface. So it hindered us to be quantitative. And the good thing is that we can solve or resolve this peak overlap using natural abundances. And this is what we have done actually in the work that we have submitted recently on the Journal of Microscopy and Microanalysis, where we have used the natural abundances to resolve the peak overlap between copper, zinc, and sulfur-2 on the mass spectrum. And of course, correcting a mass spectra, it's an over-constrained problem. So the problem is that we have more equation than solutions. And we have also this, so the problem is we have this formula in the center. So we have, here is representing natural abundances. Here we have the real ion counts. And here we have detected ion counts. And we can use different methods to solve the peak overlaps. And there were been two main methods published until now. The first one is the least square method, and the other one, the second one, is the maximum likelihood estimation. The advantage of the least square method is that it has a superior speed. The problem is that with the least square method is that it's not that accurate actually. So if you want to resolve peak overlap in a very defined little volume, this then will be not that accurate. By applying the maximum likelihood method, then we are able to accurately resolve peak overlap in a very small volumes. And this method had been applied actually for resolving peak overlap at the interface region. And we have shown nicely and explained nicely in our paper submitted recently to the Macroscopy and Microanalysis journal. So this method can be applied for 1D concentration profiles, where, of course, we don't care too much about the interface, if it's straight or curvy. We just want to find out how the elemental distribution takes place at the interface. In the case that we have a very curvy interface and then resolving also the roughness of the interface start to play a big role, then performing a proximity histogram really starts to be very important. And therefore, we have implemented these methods for both, for the 1D concentration profile and the proximity histogram. The disadvantage of the proximity histogram is that the value that we get, it's always dependent on the isosurface that we have generated at the interface. So we need to be always very careful when we deal with the generation of the isosurfaces. So when we deal with complex materials and interfaces, we need to actually perform 4 important steps. First of all, we need to identify all ions on each side of the interface. Of course, if we miss some ions or we assign wrongly some ions in both sides of the interface, then we will not have anymore a very robust result. Then we need to choose ideal analysis method for the data. So you need to ask yourself what you are really interested on. Do you really want to perform proximity histogram or 1D concentration profiles? So you need to correct the composition and solve the overlaps, and this correction need to be done on the both side of the interface. And of course, you need to verify at the end your results. So you need to choose different isosurfaces. You need to change the area of the analysis. You need to compare the 1D concentration profiles with proxygrams, and always double check that your results are robust. So all these steps have been implemented in a user-friendly software, which is called ePOSA. And the functionalities of this software are shown here on the left-hand side. So it's really very user-friendly. So it can be used by anyone without having deep knowledge on programming. It's really expandable. It has an easy data selection. It can also not only resolve the peak overlap on the mass spectra, but it can also analyze the multiple events. So this is a functionality that it's impossible to do with IVAS right now. And we can generate definitively proximity histogram with overlap solving. And how does it look like, this software? And you are free to ask us anytime when you want to use it, and it's free of access. So I wanted to give you here an example of an interface of a PN junction which had been analyzed using the ePOSA software. So why it was important to investigate this interface? Actually, the ePOSA had been developed because of this need. We wanted to find out what is the composition of a PN junction. It had been long time stipulated by the solar cell community that at the CIGS surface, we have a copper depletion region. And this copper depletion region would mean that we have a preferential segregation of copper vacancies on the CIGS surface. But then was the question, what happens when a buffer comes and it's deposited on this absorber surface? And therefore, knowing exactly what is the composition of this PN junction or this hetero interface would be really very important for the community. And first of all, from the uncorrected proximity histogram here, we see clearly that the zinc content inside the absorber, it's really very low, so lower than it should be expected, so 50 or a bit lower. And we see also that we get a lot of selenium inside the zinc sulfur oxide, and this is because some overlap between selenium molecular ions and sulfur molecular ions. And by correcting the proxygram, we see clearly that we have zinc content which approaches 50%, and then we have almost no selenium inside the zinc sulfur oxygen buffer layer. So right now we are confident with these results. They also fit very nicely with what have been observed by other characterization techniques. And we know that this method is pretty reliable to resolve peak overlaps on the mass spectra on a very defined volumes. So the key conclusions for this part are the following. The presence of molecular ions, of course, enhances the probability of peak overlap on the mass spectrum. This peak overlap can be solved by using natural abundances, and I showed you how the method maximum likelihood estimation can be used to actually resolve peak overlap on the proximity histogram or 1D concentration profile. So right now, I also showed you that it is possible to analyze interfaces between two compounds where we have a big probability of peak overlaps. And these interfaces can be easily analyzed using our own design ePOSA software. So during this last part of the lecture, I'm going to speak about multiple events, not really as an artifact during the atom probe measurements, but as a fingerprint of an unconventional bonding mechanism. So we have two possible phenomena taking place for the multiple events. So what are multiple events? Multiple events occurs where more than one ion hit the detector during a single pulse. So basically when we have a pulse, we have not only one ion which is field evaporated, but several ions, two or many ions evaporated and then collected on the detection system. So there are basically two processes. The co-evaporation process, which is simply the fact that when the laser hit the tip, we have the field evaporation of two or many other hits, and the molecular dissociation process, when the laser hit the tip, we have a molecule which is field evaporated, and during the path, this molecule is going to dissociate, and very often we end up to have multi-hits on the detection event histogram. So if we recall now the field evaporation process, this is simply a thermally activated evaporation process of a charged ion over an energy hump. And if we want to describe the field evaporation rate, this is simply an Arrhenius model where the Q and F represent the activation energy. So this activation energy is actually the energy necessary to break the bond and to ionize the atom released, and then to field evaporate this atom as an ion. So if we speak now about breaking the bonds, so what is the energy necessary to break the bond? And actually, many people have thought, okay, this energy is simply given by the bonding energy, which is the work necessary to remove an atom in a field-free space. Now we know that the atom probe experiments are performed under a very high field. So in the presence of a field, the bonding energy of a surface atom is increasing by a delta lambda value. And this has been proven by the Miller and Richard Forbes, that a bonding energy in the presence of the field is increased by a value delta lambda, which is given by the product between the atomic volume and the field. And they have done some calculations for the rhodium material, and they have found for a field of about 41 volt per nanometer that we have an increase of the bonding energy to the field of about 0.64 electron volt. So now, if we think about the bonding energy in the presence of the field, we have the sum of these two, and then we end up with a higher value than the bonding energy itself, which is about 6.39 electron volt. So another important aspect is to realize that the bonding energy vary from material to material and depend on many material parameters like conductivity, electron polarizability, and this parameter I'm going to talk about them in a few slides. So I wanted also to describe the possible bonding types that we can encounter in material science. And I divided them in two groups based upon the behavior of electrons. And we have the localized chemical bonds here on the left-hand side. And we speak about the ionic covalent bonds. And we have delocalized chemical bonds where we speak about metallic bonds. For the ionic and covalent bonds, the electrons are concentrated on a limited region of the molecule. So we have in general a very high electronic density. For the metallic bond is the opposite. The chemical bonds are not associated only with a single atom, but with several atoms or chemical bonds. So we have in general a very low electron density. But within the same class, we find also variation in terms of electron behavior. So if we speak about the ionic compound, we see, for example, for sodium chlorine compound, that we have a transfer of the electrons from the sodium atoms to the chlorine. So for the ionic compound, we have a very high electron transfer process. Now for the covalent compound, this is not the case. In this case, the electrons are shared between the atoms. And if we take the example of carbon hydrogen 3, we see that the electrons are shared between the carbon and the neighboring hydrogen atoms. For the metallic compound, the metallic bond actually can be thought of a cloud of positively charged ions, which is immersed in a cloud of balanced electrons. So the concept of metallic bond is also very different than the ionic and covalent bond. So to show you actually the implication in terms of atom probe experiments, I show you here how the bond breaking take place for two compounds, for the antimony selenide and antimony sulfide. And here I show you the correlation histogram. So many of you are familiar with this correlation histogram. It simply gives you the distribution of the multiple events in a 2D map. And we see that we have many dissociation tracks here available on this map. And I presented also the dissociation tracks and dissociated molecules which have been formed, and for both compounds. And we see nicely that for both compounds, we end up to have antimony sulfide or antimony selenide ionic compounds. So these compounds are really very stable and they are not going to dissociate further. And the question is why? So why some of the molecules are going to dissociate and some of them not, are going to be stable? Are the bonding between certain atoms more robust than others? And to have a clearer map, I show you here some DFT calculation done on antimony selenide. And it had been found that we have indeed 4 different bonding lengths in antimony selenide. And 3 of them have higher bonding lengths and only 1 of it have a very short bonding length. And this might be the reason, because we know that shorter is the bonding length, stronger is the bonding at the end. Then this might be actually a reason why we end up to have very stable molecules during the dissociation of in the atom probe experiments. Another example is shown also here on this slide, where I show compounds which have exact similar chemical composition but different structure and different also bonding mechanism. So we see that for the green one, we have a total molecular ions of about 40%, but for the second one, although we have exactly the same chemical composition but different structure, there is a amorphous compound. And we know that also this is a covalent compound. We have a much higher fraction of molecular ions. And the same have been observed for other compounds which have different chemical composition but different also chemical structure. And we see nicely that the same behavior is repeated 3 times. So for the rhomboeder structure, we got always a lower fraction of molecular ions than the covalent structure. Now the rhomboeder structure is believed to have this novel bonding mechanism, which is a weaker bonding, much weaker than the covalent bonding, and of course would be a nice explanation why we end up to have a lower fraction at the end of molecular ions detected on the detection system. Now let's speak about the theoretical probability of multiple events. So the probability distribution function, it's given by an exponential law, a Poisson law, which is actually depending on the mean time required to detect an ion, tau d. Now, if we work further on this exponential law, we can develop the probability of multiple events, and we can define it depending only on the detection rate of the n atoms. And if we then take, for example, the detection rate of about 1%, what we usually use for the atom probe experiments, we see that we end up to have a theoretical probability of multiple events, which is rather low. And this is 10 to the power -5. So this is a very low probability. And let's compare now with the experimental value. So the green line represents the theoretical value, and this is very low. And if we compare with the experimental value, we see that we have a really very strong shift. And this had been shown also by doing simulations that we end up to have a very high fraction of probability of multiple events, much higher than it had been proposed theoretically. So actually these two results show that the evaporation at the tip surface does not really follow a random statistical behavior. So actually the atoms are sitting within the terraces. We have position which it has a higher field. So we have higher probability to get field evaporated than other positions. And this is why actually the field evaporation process, it's pretty complex behavior. So when we deal with multiple events, we need also to take into account the detector limits. And the detectors are limited in number of recordable events in space and time. And this graph shows actually the fact that we have regions where the multiple events cannot be unfortunately detected. And but about that, about the dead time and dead zone, Gerald Dakoska is going to give a lecture about that. And this is the lecture number 6. Therefore, I'm not going to speak too much about these problems. So what are the possible origin for the multiple events? So they are, as I said, correlated evaporation or molecular dissociation, but we know that there are some phase change material where we have very little or the absence of dissociation tracks on the correlation histogram, which means that molecular dissociation alone cannot be the single reason for the multiple events. Then we have also artifacts which can explain the formation of multiple events, which are DC evaporation, surface migration, and burst evaporation. Knowing that in our case, for example, that the parameter used was the optimal one, this kind of effects had not been observed during our experiments. Therefore, I'm not going to speak too much about these artifacts, but there are papers in the literature where they discuss this possible reason as a reason for the presence of multiple events. So the question was also that if these multiple events are correlated in time and space. And there is a very nice work done by Christian Baki in Rouen University, where they calculated and simulated actually the distribution of inter-impact distance of the multiple events. And actually they found that the distribution of the inter-impact distances has two main contributions. So it's an overlap of two main contributions. So one is related with the ions coming from the same emission seat. So these are our correlated ions in red, and ions related to the stochastic evaporation. So, and these are completely uncorrelated ions. And if we now develop further this concept, we can recall the work of Batisco on gallium antimony. And the authors have been shown that actually we have the distribution on the distance distribution map, which shows two main contributions for the multiple events. So the first contribution is due to the co-evaporation process, and the second distribution is due to the molecular dissociation. So now the authors had claimed for the gallium antimony compound that the correlated field evaporation and field dissociation are both occurring simultaneously. So simultaneous impact are very closely situated on space, but also in time. So we have a very strong correlation in space and time. to find this time correlation, they have just performed the distance between the impact for the successive pulses. And they found it did a very strong correlation also in time. Now, is it this behavior true for all class of material? That can be this concept extrapolated for all material investigated by the atom probe tomography, which show a very high multiple events. So I just wanted to recall you here that the gallium antimony is a covalent compound. It has a sp3 bonding compound. I give you here another example, which maybe resemble a bit to the gallium antimony, but it's also different. This is the hexagonal germanium antimony telluride. It has a probability of multiple events, the experimental value of lower than 30%. We see here on the detection event, on the correlation histogram, that we have dissociation tracks. So we have the formation of molecular ions, and this is nicely shown here by the second hump on this distribution histogram. But we have the peak which corresponds to co-evaporation, which is even higher than the second hump, which means that still the main phenomenon which takes place in this case, it's co-evaporation. If we look now on the successive pulses, we found a very weak correlation in time between these multiple events, but this also is not completely down to zero. So if we go now to another material, so yeah, I wanted also to say that by using the IPOSA software that I have presented before, we are also able to subtract the from the multiple events that we get, to subtract the multiple events associated to the dissociation phenomenon. So what we have here in this correlation histogram is that we have points which correspond to the sum of pairs M1 and M2. So the dissociation tracks actually show the origin of the ions. So we can visualize actually the origin of the multiple events. And the dissociation tracks, thankfully, due to the IPOSA, can be filtered out from the dataset. And what we get as a correlation histogram, which will look at that. And then we can extract back the number of the multiple events which are not related with the dissociation phenomenon, but only with the co-evaporation phenomenon. And this concept has been used to determine the probability of multiple events for material which have shown very high values. And this is the case for the rhombohedral germanium antimony telluride, where the experimental probability of multiple events was found to be higher than 60%. In this case, we don't see any more two hump. We just see one single peak, which corresponds to the co-evaporation phenomenon. And we see also that these multiple events are also correlated in time, but much weakly than the one correlated in space. So what we can see is that we can still observe a very high probability of multiple events, although we don't have or dissociations track on the correlation histogram, or we have very weak dissociation tracks available there. So that means this material should have also very particular properties in terms of physical properties or bonding properties, which can be nicely correlated with the unusual bond breaking behavior during the atom probe experiments. And if we are looking now on the different properties, which are bonding properties like electrical identifier, like the conductivity, then the effective coordination number as a structural identifier, and effective coordination number is determined simply by counting the other atoms to which it's bonded. Then we have as an optical identifier the optical dielectric constant, which is a measure of the dielectric polarizability of a dielectric compound. Then we have the Born effective charge, which describe the chemical bond polarizability. And we have finally the Grunizer parameter, which describe the anharmonicity, bonding anharmonicity. So what we can see is that for the class of material where we have very high probability of multiple events, we observed properties which are very, very different than the typical ionic or covalent compounds. So typically we have moderate conductivity, although for covalent and ionic we have pretty low conductivities. And for metallic compound, of course, we have very high conductivity. The octet rule is not fulfilled, like for all the other compounds. The optical dielectric constant is very high, and of course, this is a very important message because this, of course, is directly linked with the field penetration depth, and I'm going to speak about that a bit later. And the optical dielectric constant is low for the other covalent or ionic compound. We have a very high Born effective charge and a very high Grunizer parameter. And for the ionic compound and covalent compound, these parameters are low. So definitely we can say that the material which are situated in this region or within this, which has this particular properties, are different than ionic and covalent compound. Therefore, in our group, Professor Matthias Wuttig had been developed the concept of a new bonding in this material class. Now, the different bond breaking mechanisms observed during the atom probe experiment can be considered as another fingerprint for this particular class of materials. So let's go and talk about that. So for that, we took two different compounds, and we have compared actually the evaporation process in the atom probe, the bond breaking process. And what we have observed, so if we take hexagonal germanium selenide telluride, which is a covalent compound, and we have a laser coming on it, we see typically that we have a high probability of single events, and we have a very low probability of multiple events. Now, if we take a rhomboedral compound, which is the compound supposed to have these particular properties, bonding properties, when we have the laser coming on it, we have typically a very high fraction of multiple events. And this is about 62%. We see also nicely that these multiple events are homogeneously distributed over the detector event histogram. So also if we take compounds which have this similar composition, so like antimony telluride, antimony sulfide, but have different structure and different bonding mechanisms, we see that having similar composition doesn't have to have similar behavior in terms of bond breaking inside the atom probe. And we see typically that the materials which has the unconventional properties show very large probability of multiple events, although the other covalent materials or ionic materials shows a pretty low probability of multiple events. And to enlarge even more the observations, we have compared actually the probability of multiple events versus the electron transferred and the electron shared. And we have performed these measurements for many classes of materials, for metallic compounds, for ionic compounds, where, as I showed you before, we have a very high probability of electrons to be transferred. For the covalent compounds and our metavalent compounds here in the green area. And we see nicely that for these compounds, we have a very high probability of multiple events, which is much higher than 60%. So which means actually that the bond breaking mechanism, it's not stochastic behavior. So it's really correlated with the electron behavior down to the bonding level. So now let's go and explain why we have an enhanced coevaporation process taking place for this particular class of materials. And to explain that, I have shown here two main compounds which are widely used during the atom probe experiment. So we have the metallic compounds. For the metallic compounds, we have in general a very small field penetration depth. We know that. We have learned that during this lecture. And the metallic bonds are also very soft. But this altogether leads to pretty low multiple events of about 10 to 20%. Now, if we take a covalent compound, we know that these are semiconductor materials. So we have in principle larger penetration depth than the metallic compounds, but the bonds are pretty strong, way stronger than the metallic bonds. So this is why also we have, in general, a pretty low probability of multiple events, and this is between 10 to 20%. In between, we have this class of material, which is called metavalent materials. And for these metavalent materials, what we have learned is that the field penetration depth, which is directly proportional to the dielectric constant, it's way superior than the metallic and also than covalent compound. So we have learned that the dielectric constant, it's very high, higher than the covalent and ionic compound. And this explains also why we have a way higher field penetration depth for this metavalent compound. And also the second ingredient is that the bonding, the metavalent bonding is rather soft like metallic bonds. So these two ingredients, high penetration depth and very soft bonds, are the one which explains actually the enhanced coevaporation process and explain why we get so high multiple events during the atom probe experiments. So the key conclusions for this fourth part are the following. So the multiple events are not only due to the molecular dissociation process. So we have seen also that some other processes can explain the formation of multiple events. Also, multiple events are not necessarily an artifact and can be really a fingerprint for the bond-breaking behavior during the atom probe experiments. So we have also saw that actually multiple events can also explain this enhanced coevaporation process which take place for the metavalent compounds. As a final conclusion for this lecture, I hope I could convince you that thermal effects are important aspects that need to be considered when working with a semiconductor material, also with a metallic material. I hope I could convince you that the field effects are pretty important to be taken into account. And liquid metal ion source might be a possible reason for the molecular ion presence on the mass spectra, but some other phenomena need also to be further established. And this phenomenon need to take into account also what happens in terms of electronic distribution down to the bonding level. I hope I could convince you that the presence of the molecular ions and also multiple events are making our data analysis more difficult, and therefore we need to develop further tools which help us to better quantify our compositional data inside our atom probe experiments. And I hope I could convince you that it's possible to get the convoluted proximity histogram and that it's possible also to perform advanced analysis of the multiple events. And also the multiple events at the end fits very nice, so this very high probability of multiple events that we have systematically observed for a particular class of materials that fits together with the unconventional optical and structural properties and can be indeed considered as a fingerprint for the unconventional bonding mechanism, which is called metavalent bonding. So at the end, I would like to thank you for your attention, for your patience to hear this talk, and I would like also to thank to my group members and the members which had also helped me to develop the slides for this lecture. And if you have questions, we are glad to answer to your questions. So here below you can find my email. So you can anytime contact me through the email, and I'm glad to continue to discuss on this topic. Thank you very much.